If you clicked on this video, you are probably wondering what amphiphilic materials are. Oftentimes, chemistry and other related fields contain jargon like this to describe molecules that are very complex. Luckily, this term is not as complicated as it may seem. In this video, we will be going over exactly what amphiphilic materials are, examples of amphiphilic materials, and a practical reaction procedure to synthesize an amphiphilic polyester. We will then demonstrate its switchable properties by testing its ability to encapsulate red and green dyes. So, what are amphiphilic materials? Well, to answer this question, we first must understand what hydrophobic and hydrophilic means. Hydrophobic molecules, simply put, are those that fail to mix with water. This is because hydrophobic molecules contain a nonpolar structure, usually a carbon chain, that doesn't interact well with the polar structure of H2O molecules. Hydrophilic molecules, on the other hand, are those that tend to attract water due to the polar structure of the molecule. So amphiphilic materials are materials that exhibit both hydrophobic, water repelling, and hydrophilic, water attracting regions. As such, amphiphilic materials can exhibit unique and switchable stimuli responsive behaviors in different media or when in contact with different materials. These properties make amphiphilic materials useful in a vast array of applications, including food, cosmetics, pharmaceuticals, and cleaning. One common example of an amphiphilic cleaning material is soap. Soaps are typically composed of a long hydrophobic hydrocarbon chain and a shorter hydrophilic carboxylate group. The hydrophobic portion of the soap will interact with the grease, while the hydrophilic portion will interact with the water. This allows soap to clean both oil and water-based dirt and stains. Another example is liposomes, which are spherical structures made up of a phospholipid bilayer. The phospholipid bilayer has a hydrophobic tail and a hydrophilic head, which allows the liposome to encapsulate both hydrophobic and hydrophilic substances. Liposomes have been useful in many applications, such as drug delivery, food, and cosmetics. Amphiphilic materials are also present as polymers or plastic. We can synthesize amphiphilic copolymer polyesters using a condensation solution reaction. This reaction can be synthesized using the reagents polyethylene glycol, or PEG, with a molecular weight of 300 grams per mole, and sebacic acid. This amphiphilic copolymer will arrange into invertible and switchable micelles depending on which media it is dissolved in. In organic media such as toluene, the micelles will demonstrate hydrophilic inner compartments. On the other hand, in aqueous media such as water, the micelles will demonstrate lithophilic inner compartments. To make the reaction proceed in the forward direction, we will be removing water from the reaction flask using a Dean-Stark trap. According to Le Chatelier's principle, removal of water causes the equilibria to shift, favoring the products. This can allow for higher conversion, especially in condensation reactions. A Dean-Stark trap consists of a round bottom flask, a sidearm, a condenser, and a trap. The round bottom flask contains all the reagents and the organic solvent. As the flask begins to boil, the water and organic solvent, in this case toluene, start to evaporate out using the inclined sidearm. These molecules then hit the condenser and accumulate in the trap region as a liquid. Since toluene has a lower density than water, the toluene and water will phase separate, leaving the toluene at the top and the water at the bottom. Excess toluene will drip down the inclined sidearm and back into the boiling flask. If too much water has accumulated in the trap, you can use the stopcock to empty it into the beaker. To isolate the amphiphilic polymer, the toluene solvent needs to be removed via rotary evaporation. The formed polyesters should be a viscous fluid that looks colorless or slightly yellow. Now, to demonstrate the amphiphilic nature of the polyester, we created two solutions. One consisted of water plus Sudan red dye, and the other consisted of malachite green dye with toluene. We created two of each solution, one to be used as the control and the other to be used with the polyester. Once the amphiphilic polyester was added to the two vials, the solutions were then shaken and allowed time to settle. The following solutions are observed. As seen in the figure above, the polyester encapsulates the Sudan red dye while in the water medium. On the other hand, the polyester does a poor job of encapsulating the malachite green dye. When you compare the two solutions, the one without the polyester is much clearer than the one with the polyester. This demonstrates the invertible switchable micelles of the polymer. While in the organic media toluene, the polyester exhibits hydrophilic inner compartments, while in the aqueous media water, the polyester demonstrates lithophilic inner compartment. Hopefully this video has given you a greater understanding and appreciation for amphiphilic materials. In short, amphiphilic materials are those that have both hydrophobic and hydrophilic regions and are thus useful for many applications. Maybe the next time you look at a soap bar, you'll understand the science behind what makes it possible.